This is the second part of 12.1, and it's all about pressure. So we're going to further explore the idea of pressure, what is pressure, and do some calculations with pressure. So first of all, what is pressure? Pressure is the force per unit area. Pressure just results from the collision between gas particles. So they hit the walls of the container of whatever they're in. So we can obviously increase pressure by increasing how fast the molecules are moving. So if they're moving faster, they're going to have more collisions. We can also make the container smaller, so there's less places for them to move. Pressure, to me, you can kind of think about like a rock concert. You go to a rock concert and you're down front by the stage, and of course, like if there's a song that's not very good, what's going to happen? You're not going to move as much. So there's not a lot of people standing around. There's lots of room to move. So the pressure's it's kind of like with gas molecules. There's not going to be a lot of pressure. There's lots of movement. Room to move. There's kind of associated with that. Whereas if there's a song that comes on at a rock concert where it's really it's the best song the band has and everybody loves it, and so what's going to happen? Everybody's going to crowd in around the stage and it's going to get really excited, and there's going to be it's going to really packed, and there's going to be lots of collision. There's probably going to be moshing, and so there's lots of pressure. There's lots of collisions, and so it's really just highly intense. And so that's what I think about with pressure is kind of getting that mindset put in there. There are two kind of types of pressure. First of all, there's gas pressure itself, and this is just the result of the collisions between the gas particles themselves. If there's obviously no particles, then there's no collisions, and so you have to think about it too, that what happens when you get a gas in a vacuum where there's no air. You're not going to have any collisions. Then you have atmospheric pressure, which is collisions of the actual air molecules themselves. And it decreases the higher the altitude gets because there's less air. So you have the collision between gas molecules, air molecules. Atmospheric pressure is also weather dependent. So you've got the gas particles that happen more like in a vacuum type system where there's not the air, and then you've got the atmospheric pressure that happens when there are air molecules happening. We use a device called a barometer in order to read atmospheric pressure. It was invented by a famous scientist named Torricelli. The video here shows kind of a couple of old school barometers. So you can see that on the right hand side is what a barometer is basically made up of internally, the idea of what a barometer is. It's a tube put into some kind of usually liquid, some kind of, in the old days of course they used mercury. Now they're more alcohol based because we don't use mercury anymore. But the idea is that the atmospheric pressure pushes down into some kind of liquid, and that liquid pushes down up into some kind of sealed tube. And so as the atmospheric pressure pushes down into that liquid, the liquid within the sealed tube pushes up. And so as the pressure builds up on that external liquid, the liquid inside the tube goes up. And so on days where the pressure is higher, you can see the atmospheric pressure is going up. And on days where the pressure isn't as much, obviously the liquid in the tube is going to go down. And so that's kind of the general gist of how a barometer works. There are lots of different units for pressure. These are the most common ones that we'll use in this class. We have millimeters of mercury. That comes from the idea of that you measure from the barometer how much it went up in millimeters on the barometer itself. So did the millimeters of mercury rise up 1 millimeter, 2 millimeters, whatever. So, and then they went a step farther and they said, instead of saying this is a millimeter of mercury, we're just going to call that a torr. So actually a millimeter of mercury and a torr are exactly the same thing. Then we have a standard atmosphere. We call that an ATM. That's the most common unit that we'll use in this class because all of our gas laws, the actual calculations that we'll be doing, require ATMs. So we'll be basically turning everything else into ATMs. So we'll be using millimeters of mercury and torr doing calculations to get those into ATMs. The SI unit for pressure is actually the Pascal, after the famous scientist Pascal. Here in the United States, we use pounds per square inch, PSI. So like if you go and you need to fill up air in your tire, you need to find out the pressure in your tires, that's in PSI. So I wanted to include that so that you understand that, hey, this is the American unit for pressure. Here are all your equivalency statements. So if you need to get from one type of pressure to another type of pressure, you've got all of these. So you notice that the ATM and the to torr and the ATM to millimeter mercury are the same because the millimeter mercury and the torr are the exact same thing. And again, by the third statement, you notice that the millimeter mercury and the torr, again, are the exact same thing. So you'll use these, and in the next little segment of video, I'm going to walk you through how to basically convert a basic pressure problem.
Alright, so now we've seen some different units of pressure, so now let's look at how to get from one unit of pressure to another unit of pressure. So we're going to do some basic conversions. They look a lot like gram to mole conversions, or basic, even we could even go back to doing some of our basic like meter to kilometer, some of those kind of conversions. So they're not even as difficult, I think, as a gram to mole conversion. But they'll use those equivalency statements that I showed you earlier in the video. Like for example, the first one that we're going to do uses that 760 torr equals 1 ATM. That's going to be necessary. We'll need that in order to do the conversion that we're going to talk through. Because I'm going to ask for you to take 781 torr and change that into ATM. And so that's why it's going to be necessary in order to obviously, figure out how many ATM that is. So if I have 781 torr, I'm going to write a fraction, just like we did with gram to mole conversions. I have a fraction here. So that means I'm going to put my torr on bottom, ATM on top. So using that top equivalency statement, the 760 goes on bottom. The 1 goes on top, because these numbers stay with the proper units, right? So the 760 has to go with the torr, the 1 has to go with the ATM. So torrs cancel. Alright, so notice 781, 760 on bottom. So this is going to be a division problem. So we're going to divide it out, plug it in our calculator, do the math. So you get like 1.02763, and you get a few more numbers in there. But of course we're concerned with this number here, the given, which is 3 sig figs. So 1.0 and round it up to 3 ATMs. And so that's a real basic conversion from torrs to ATMs. That's what you're going to be doing with those basically equivalency statements, going from one pressure to another. It's going to be important to be able to do these pressure conversions in order to do gas laws. When we go through and do the ideal gas equations, you're going to have things in ATMs, or you're not going to be able to do a lot of the gas equations. Even though our units, our SI units for pressures are pascals, we have to get things into ATMs. The equations won't work, we'll get wrong values. So it's going to be important to be able to do these types of conversions.